Hey friends, welcome to Coding School. Today the question that we are having is a very interesting question, and again it's a most popular interview question as well. And this question was asked by Google in its online coding round to some of the candidates. And so so what we'll be solving is where we are just given a complete binary tree and a node, and we need to return true or false if the given node exists in the tree or not. So simple, isn't it? But wait, uh, I will tell you, what the catch in this problem, what the interesting thing about this problem. But first of all, I would like to, just clear or to clarify the thing that what is the complete binary tree. So basically, a complete binary tree is a binary tree in which, except possibly the last level, okay, every level above it, should be completely filled from left to right, okay, and and all the nodes as far left as possible. So that simply means that it should be filled from left, okay, and the last level may be incomplete, but it should also, if some nodes there as well in the last level, it should be filled from left. That is the complete binary tree, the definition wise. uh, okay, so now basically the thing, okay, that is why we are just solving this easiest question in the world is this constraint, okay. So the constraint says n can vary from 0 to 10 to 10 raised to 18, okay. So basically 10 raised to 18 means it's a very large value, isn't it? So so where basically where n is the number of nodes in the complete binary tree. So basically as I have as I have shown a just a view of the binary tree, just an example. Here nine nodes are here, but it can be up to 10 raised to 18, okay. It can be so large tree, and we are just given a node. We need to find out whether it is existing in this particular tree or not. Simple. Okay, so cool. So basically, if I would have been given like 10 raised to 5 or max 10 raised to 8, 8, okay, then I could even solve it in simple one go, okay. Just a recursive call, just find out whether it is existing in the left subtree or right subtree, and similar for every each and every node in the binary tree, and I can simply end up with the solution of big O of n. Cool. So let's try that as well quickly. Then we will move to our optimized code. Actually, let me tell you that what did I mean. Let's take the key as well. Okay. Yeah. Cool. So basically, we need to we are actually moving with big O of n approach. Okay, where we are assuming that the upper bound of n is not 10 raised to 18. Instead, it could be like less than or equal to 10 raised to 8 or something. Okay, cool. So now let's solve this problem. Cool. So basically, we first of all we need to get the numbers from user, that and one more thing that I would like you to know. Let me just quickly write it. Yeah. So let me tell you, in the very beginning that one more thing is there, that the arrangement of these elements. Okay. See, the arrangement of this element is quite, very, beautiful. Why? Because see, here the arrangement are done from left to right, okay, according to their positions. Let's say here it is 1, it is present in the very left, so it is 2, then 3, then 4, 5, 6, 7, and so on and so forth. and these arrangements should be you know should be there. Okay, if there is only one node, so it should be one. Okay, the element should be one, and if there is two node, then one, then two. If three, then one, two, three. Okay, so every time if there is a tree, then you should have this tree, this kind of structure. Okay, so this is the question basically. So basically in this question you will be given the root node is one, and followed by things. Okay, 2 3 4 5 6 7 and so on and so forth, like this only. So yeah, so now let's build the tree. As we are just talking about the complete binary tree, then we can simply just build the tree. So to build the tree we must have uh, something, a structure. Okay, we are actually writing tree node because we are familiar with lit code. Cool, but we will change it according to ourselves. So now uh, the left child and the right child. Okay, so now let's define the constructor. Okay, so here I will just fill up the data with the given, and left right with null for every new node. Every time I'm just trying to uh, build a new node, there only I'm just trying to make the left and right side of that particular node is null. Cool. So for now, for my convenience, I'm just writing this particular structure and node. So basically what I'm doing is I'm trying to get the root node of root node after building the whole binary tree, whole complete binary tree basically. So let's call it build tree. Okay, so in build tree I will be passing like the complete array. What should be the starting position and what should be the ending position basically, or the last position of this. Cool. So basically I just have, let's say somehow I just have computed all the things. I just have built the thing, and I have the the tree with me. So let's now just to verify things, let's traverse just a quick traversal, then to verify whether it is actually built or not. Cool. So let me write that as well. So basically in order traversal, as we already know that we should move left first, and after finishing the left part we should touch whatever the node I am currently at. So it should be data. Okay, and after it I then only I should move to the right subtree. Cool. So I have done my traversal part as well. Now it's time to build the tree actually. So the tree should be of node type. Okay, cool. So here I'm just getting the input as the array, the starting position and the ending position, isn't it? Only that. Okay, so here let's focus on what should be the base condition, because I'm just going to write a recursive call to make the whole thing for me in a single go. So basically my starting position is always less than the ending position. That means uh, let's say my array is something like this, like 1 2 3 4 5 only. So here the position for 1 is 0 and position for 5 is 4, isn't it? So whenever the left or the the lower bound is will be equal to the size of the array, or we can say if it is greater than the last position, then only I should return 0, because I have no more element to add to the tree, isn't it? So whenever my I will be greater than n, then I should return a null. Cool. Otherwise let's just build a virtual root. Okay, which will be like the current element of my array. So I will call array of I to build up that node for me. Cool. After building of it, let's fill the just recursively, because I have already built the current node, but I do not have the left and right subtrees of this particular node. So I just want to recursively build all the nodes which I have built the as I have built the current node basically. So let's build it recursively. Okay. Cool. So what will be my starting position for the left child? See, if there is a child, let's say one. Okay, I'm just taking the root as one for now, just an example. So what will be the left child of it? See, the left child will be for sure will be, let's say the one is at index I. I'm just looking for the the formula or something like that for the left child. It will be 2 into I. Or if I just taking care of the indices, okay, then I would say that most preferably it would be 2 into I plus 1 is the left child and 2 into I plus 2 is the right child. So as I am actually taking care of the indices right here, that is why I am just writing 2 into I plus 1 for the left child, and I will be defining 2 into I plus 2 for the right child. And n will be same. Okay, n will be remain as it is because it will not going to change in any way. Just to validate. Okay, cool. So okay, so here it will be right, isn't it? Cool. After building recursively all the left and right, what I should return? I should return the root for every state. Okay, cool. So here we have successfully built the tree, and here I'm just trying to find out the path for it. So let's quickly verify. Okay, let's quickly verify the things. Okay, so it is, does it just or not? Okay, cool. So let's say I have 5 node. Okay, I'm not actually verifying anything. I'm just trying to find out whether the tree is built or not. So let's say 1, 2, 3, 4, 5. So what it's supposed to return me? It should return me like 4, 2, 5, then 1, 3, isn't it? Let's say 1, 2, 3, 4, 5 only, and 1, 2, 3, 4, 5. Okay, these nodes are not there, not here in this particular example. What it should return in the another traversal? It should return 4, 2, 5, then 1, then 3, isn't it? 4, 2, 5, 1, and 3. Cool. So it worked for me, and now what I have to do is I just need to remove this particular part because the tree is now done. Now my work is to actually verify whether it is present or not in the most worst scenario. That means I will be moving in big of an approach just to find out whether the node is present in either side. Okay, so is there. Cool. Is there. So is there. So root, I will pass the root and I will pass the key. Okay, so if the node will be there, then it will simply going to return me a boolean value, whether it is there or not in true or false format. So cool. So quickly write it down. That's a key. Okay. So here, what will be the best case? So the best case would be, for example, we have no tree. As I have mentioned here, the lower bound will always be 0. Okay, it can be 0 because we might have no tree at all. So in that case, what should you do? So in that case, we should return false because let's say we do not have any tree. Let's say we do not have this one. Okay, and I'm just asked to find out whether in the given tree one is present or not, because I have nothing. I have no tree. So how can I just return anything is present over here or not? So like that. So if there is no root, I can just simply return a false. Okay, cool. Otherwise, what I can do, if somehow I find out that in my, wherever I am at, okay, so in that particular node, if I find out that that particular node is nothing but my key, then I should return true, isn't it? Otherwise, I should, move both left subtree and right subtree to search this item for either side, okay, to find out wherever it is, So basically, I should return is there for root left and pass the same key, or why I'm writing or, because it can be anywhere, okay. If I just write and let's say for this particular root, I'm just calling this particular subtree to find out and this particular subtree to find out, and I in the between I'm just writing and. So what will be done, let's say I'm just searching 3, so 3 is right here, okay. All the values are unique as well in it because they are arranged according to their numbers. So this particular subtree will return 1 is false because 3 is not here, but 3 is right here, so it will just return 1, and 1 and 0 is 0, isn't it? That means I did not find in that value in my tree. But if I just, if it returns 0 and if it returns 1 and I am just trying to OR them, then it will just give me 1, because any in any one side I just found out this particular value. That means is that. And I should, I should traverse the right part actually. Okay, so basically it will be just going to solve this particular problem for us. Let's say we have this particular tree, okay. Let's say there are 9 elements and we are dealing with let's say 3, okay, cool. It will give me 1, as you can see right here. It is actually returning me 1, okay. But if I just test for the, let's say 10, there are 9 elements but I'm just looking for 10. If it is there, okay, then it will just return me 0, as you can see. Okay, if you are not able to see, I can write something like this. Found. So basically, please understand it in this way. If it returns 0, that means the element is not there. Cool. Okay, so let's say 9 and I'm looking for 10. 1 2 3 9 and found is 0. Cool. But if in the same case I'm just trying to find out the value, let's say 4, okay, and 1 2 3 4 9, then it is finding the particular value. It will work, okay. So this is the solution basically in the worst case, because I am looking at every possible I'm going to the every possible node to find out whether it is equal to the key or not. So it will work for at max 10 raised to 8 or 10 raised to 7, but it will no go beyond it, okay. It will not going to work beyond it. Let's say we have 10 raised to 18, so will you think that it will just go work? Because it, in this approach we are just trying to touch each and every node every time, and we are just returning the whole thing, whole bunch of thing as a cumulative answer. It will not going to work because it is very very high tree, very very large essentially. So what will we do here is, see, the logic is very interesting, okay. You just need to stay with me throughout the session. I'll just tell you, you will just enjoy it, okay, I promise. Anyway, so basically, first of all, we need to handle something. Let's say we will not going to build anything if n is equal to 0, okay. If it n equal to 0, then we will say not found, or we can simply just return -1, something. It will just denote that yeah, the element is not there, okay. Else we will do something to it. Cool. Okay, now Okay, so found is equal to, okay, basically, hmm, basically if it is there only and is, you know, equal to 1, okay, if it is there and no, if it is there, okay, just let me remove it. Actually, I was trying to how to actually represent it. Okay, if it is there, it will just return 1, or otherwise it will just, you know, print 0. Cool. Cool or not? Okay, cool. So basically, what my point right here is, so basically, let's imagine this particular tree, okay, and let me pick my pen as well, and I am just, you know, trying to find out whether 9 is existing in this particular tree or not. So to actually verify whether 9 is actually present here or not, what I can do, I can simply find out the path, you know, from the root, I mean from 1 to 9. And if the path exists, if I follow the path from root to 9 and I find at the end that 9 exists, then that means, yeah, it is existing, or it will not. So what I'm saying basically is, if I somehow find this particular path, that means to reach 9, I should take a left from 1 to 2, then I should again take a left, and I should take a right, isn't it? To get, you know, to find out 9. So let's say for 10, so because 10 is not here, but if it would be here, then it should be in the left side of 5. So to reach here, I should take a left from 1 to let me pick another pen, I mean another color basically. Yeah, to reach 10, I should take left turn 1 to 2, then I should take a right turn, okay, from 2 to 5, then I should again take a left turn from 5 to 10, okay. So in this case, if I just follow this path, left then right then left, I would end up with a null node, okay. uh, I would end up with having a null node basically. So if it is null, so that means that I have no children as well. I have no children, okay. So so this is the case. For example, I could have 11 right here and 12 in this particular position in the left node, left side of 6. So if it is the case, then also I could, you know, end up with nothing. So this is the logic basically. So the now, you know, let's talk about the time complexity of this particular algorithm. See, let's analyze the time complexity. How, you know, it will be depending on how we are finding the path, okay. So basically, let's say the example is 9, okay. Let's say anything, let's say 4. So let's say the 4 is present at ith index, okay. So what will be the the left side of it? The left side of it will be 2 into I, sorry, 2 into I, isn't it? Because the root node is starting from 1. And what would be the right side of it? It should be 2 into I plus 1, isn't it? So basically, if it is 2 into I and I am just finding I here, so it will be, let's say there is a value k, okay. There is a value k, and I'm just finding whether it is in the left side or right side, okay. So 2i, if it is equal to k, I'm just finding out the I, then I should be equal to k by 2, isn't it? So if the division value, as it is, you know, it has nothing, I mean extra, as here, 2i has nothing extra as 2i plus 1, because right here there is only one extra one, okay. So it should give me a completely what to say, it should give me the value where the floor and the seal of this particular division k by 2 will be equal, okay. If the floor and seal value will be equal, then only I can say, so basically this is the left side. So what actually I'm saying, let's say I'm just finding in which side 8 is belonging to to its parent. Okay, so if I just dividing 8 by 2, it will give me 4. Okay, and floor value of 8 by 2 and seal value of 8 by 2 is again equal. Okay, so it will be in the left side. So if I talk about the 9, then the floor value of 8 will be, so basically the division is 4.5, isn't it? 4.5. So if I find out the floor will be 4 and the seal will be 5. So it will not be equal anymore. So if I am talking about 9, then the equality actually fails. I mean the floor and seal value are different. So that is why, so basically let's understand why this is so. So this is because there is one more, um, there is an extra one in the right side. Okay, then it's left side. So that is why the floor value is again an extra one. Okay, just one more than the floor value, the seal value basically. So we can just say that yeah, this is the rightmost element. So in this way, if I just keep on dividing, keep on dissecting things, okay, divided by, let's say I'm at 9, I'm just dividing it by 2, then I find that I am at the right position of 4, then I must write r in my string. Similarly, I'm at 4, I'm just trying to divide it by 2 to get its parent. I'm at the parent, but I'm again I'm at the same time I'm at the left of this parent, and so on and so forth up to unless I find n, until I find n basically. So I will just keep on dividing it by 2. So and at last actually I find the string containing the path, basically the direction, but the direction here is in reverse order. That means it is from leaf to, or that particular node to the parent, I mean to the root basically. But I need to check whether this particular element exists. I need to move from root to that particular thing. That is why I just need to reverse this uh, you know the string, enter string. So as actually I'm just keep on dividing things, so that is why the whole process will take big of log n time. Okay, and as you can see, the while dividing the things, I'm actually storing the direction as well. So it will again take big of n extra space. Okay, to find out the thing. So basically, this solution will be big of n in time complexity, and the space will be big of sorry, the time complexity will be log n, and same case for the space. Cool. So let's quickly remove all this thing. Let's code it out. Okay, it's a very easy solution, and okay. So basically, what will we do? Okay, that's our concern, isn't it? So here, basically, what will we do? We will just declare a string called path. Okay. So this path will be responsible for getting the whole path in reversed order or in the correct order from root to that particular given node. Okay. So here I will try to get the path while key is greater than 1. So basically I do not want the, so see, there is no path from, somewhere to the root. Okay. Somewhere means the above level of root, because the root is already at the above level. Okay. So if somebody ask me if the in the tree, if that particular root node exists or not. Okay, so there is no path to reach the root from the root, isn't it? So that is why we can simply just uh, just the string will be empty. So what is an error? Okay, it should be capital. Cool. So the path will be, as I have already explained to you clearly, that it should be follow some criteria. It should it's float. I mean its floor and seal value should be equal in order to just tell it that it is the leftmost element. Otherwise it will be the rightmost element. So if this is the case, then I could say that yeah, it's the leftmost, otherwise it is the rightmost, and in this way, and I will just keep on dissecting the things. Okay, cool. Now I have found out the path. Okay, cool. So after finding the path, basically I just need to reverse it, isn't it? I just need to reverse it, because actually what I have got so far is the reversed order of path. I mean reversed order of direction from the node to the root. But I just, in order to verify things, I just need to traverse from root to that node. That is the whole idea. Okay, now my the entire string is reversed. So here just okay, cool. So what I need to do is I need to traverse. Okay, the string is reversed basically. I just need to traverse the entire string, and just need to follow the path from root to that node to verify whether it is existing or not. Cool. So what will I do? I will simply check if my direction is left and the left child is also exist. Okay, then only I should tell my root to reach left, to just shift to its leftmost position. um Else if the direction is basically right. Okay, I'm sorry. Yeah, and there is a right position also existing. In this case I'm not, please not. Okay, just go to the right part. Okay, cool. Else, what is the meaning of else here? The meaning of else here is not about L or R, but about this particular position. Okay, if I have, let's say, encountered a path, let's say L, as I have shown here, you that, let's say, there are total 9 elements, but I'm looking for 14th. There should not be any element, okay, in the tree. So but there would be a path, isn't it, to reach 14. So in between, if I just found out there is a direction to reach 14, that is current direction is to take left. Okay, the because the the parent of 14 will be 7, so from 7 I should take the left. Okay, so but in left there is no left, so it will fail right here. Again it will just it will not going to execute this particular condition, so it will just come to else. So in this particular thing I just came to know, so it is not existing anywhere, so I will just return 0, telling that it is not existing. Otherwise I should return true or 1. Why 1? Why I'm that sure? Because I just had started with the key. Okay, and I have already got the correct path to follow to reach the given node in the entire tree. So I can say this. Or if you are not confident about it, you can simply check it. Okay, let's say the key is key. Why am I actually storing it in another variable? Because it is changed. Okay, the key is now changed because I have just worked with the given value. Okay, so it is now like 1 or 0 or something like that. So basically what is giving me an error? Is it okay? So basically you have to, if you are just traverse the entire direction, entire path, then you are somewhere and you just want to check with if the current node is the key, is my key, which I was looking for. Okay, if the data is equal to the k, then only you will just end up with the conclusion, or you can reach to the conclusion that yeah, I just have found out the node in my tree, otherwise not. Cool. So yeah, so this is the solution basically, and cool. This is the thing. So let's quickly examine whether it is working or not. So let's say I have like 13 node, okay, and I'm just looking for let's say 7. Good. Okay, so it is giving me 1. That means it found the node, okay, among these nodes in this particular complete binary. But what about this case if I would look for 16? Okay, let's check. It should give us a not found type of thing. So let's check whether I've written correctly. Yeah, so now it is giving me 0 because it did not found anything. Okay, it did not find anything in the tree because although I have the path with me for reaching 16, but when I just I have just gone through the path to verify whether I'm going to the right direction. Then I have entered this particular condition. Okay, because though there is a direction to reach 16, just to take left from 8, still there is no left element. So that is why I have just I came here and I just made this conclusion that no, there is no such element present in this tree. So cool. So this is the solution, and the time and space complexity will be log n, as we have discussed so far right here. And this is a pretty clear solution, isn't it? It will just work for 10 raised to 18 as well. Why? Because log of 10 raised to 18, that means 18 log 10. Okay, that means very faster. Okay, so cool. I hope you enjoyed throughout the session. If you just if you would be with me in uh, you know in this 20-25 minutes, so you would simply get the idea of it. And please, I just request you to keep coding. I mean, just code it out after watching the solution. Please code it out because it is quite necessary to understand things and to get in touch with such things. That will be very helpful for you. Mm. And thank you for watching this, and make sure you subscribe to the channel, and please share the solution, share the videos with your friends and colleagues, so that it would be helpful for everybody. So yeah, so thank